in comparison to what will be the case in reality. So assuming the models are not used, and we will assume it's a point mass, which is quite common, then what will be the difference and how significant will it be? And it would, for example, make a lot of sense to find the maximum length and the minimum length. Of course, minimum length would be a square with a certain height, which we need to deduce. But if you can find that, then we can calculate the differences in mode frequency shifts based on certain length. Of course, the orientation also matters, unless it's circular on a circular membrane, in which case the only thing that matters is the radius from the origin. In other cases, the orientation also could matter. And this, of course, introduces a lot of parameters. It actually introduces 4 parameters, so that is a little bit cumbersome. But of course, I'll have to limit those parameters and take certain values. And eventually, it will all be narrowed down to just a certain way to measure the uncertainty of the measurement that you take, even from a fundamental level, if you could know everything of the subject of the frequency shift response. Of course, I also have to take into account some limitations of the setup itself, which will have another blurring effect. But with that all combined, I have a blurring effect of the mass of the protein itself. I'll have the blurring effect of the setup, which would be which I could find in papers. That's already quite well described. And I could also introduce the blurring effect of the changes in the shape and how we cannot really know this. So with that all incorporated, that would actually already be sufficient, as Sherman mentioned today in my presentation, for this Bachelor End Project. So that is really good, and they were actually quite enthusiastic about progress. But I did mention that I also would like to find some time uncertainty. Now, we did have an active discussion today on how the liquid chromatography could be used. Firstly, I was proposing to model this, but that turned out to be a little bit too difficult. So the approach that we sort of included together, which would be a good approach, is to find liquid chromatography data on, for example, mass spectrometry. This is something in which, of course, I can work with Javier. And here I can actually project all the data that I have in the separation of time and mass on only the mass axis. So I compress in time so that the time variable is not relevant anymore. And then when we have these different measurements of the mass, I can convolve it with a certain function. And this function is the convolution of all the limitations which we can simply not know. So this would be, of course, as already mentioned, the variance in the mass, the difference in the measurements, limitation in the measurement, and the limitation in knowability of the shape of the protein on the nanomass sensor. But that's really interesting because we start with a certain value in the mass. So let's say we have like 200, well, that's maybe a little bit small, but like 500 daltons. So then we would have a certain protein. So we have a certain protein of that mass. The protein I can run through my program and therefore get the variance of the mass. I can deduce the density and the volume of the protein if that protein is in a database, which is sort of the plan. And from there on, I can then get a value back for the console simulation. And from that point on, I can convolve these outcomes and then get a result which would be blurred over the whole mass. So what you actually have is that instead of all these delta direct peaks, you convolve it with this one big blurring kernel, basically, which is the blurring of the mass mobility. And from there, you actually have a distribution of, hey, how well can we know the mass of protein, or how well can we distinguish different proteins if we only know the mass? And then you can quantify this and see like, hey, really, here are the limitations. And then we go back to the data, which we also have liquid chromatography. And this will then show you like, okay, here we also have liquid chromatography. Now, if we apply this blurring effect in the mass, how well can we then distinguish between certain proteins when they also separate in time? And with that, even though you do not really model anything in the liquid chromatography setup, you can still get a good result on how important liquid chromatography is on the whole setup. So with that being said, that is actually sort of the setup, and this is where it's all coming together. So in the middle, this is what I really have in mind, that you would have a mass and a time. The time variance would not really be quantified in the same way, but we can get it already from a mass spectrometry data, in where I apply the blurring effect in the mass, and the blurring effect in the time is already in the real data. So with that, I can then quantify, give good quantitative idea of how actually nanomass sensors can be applied for proteomics. And with that, my Bachelor End project would be finished. Now, normally I would now take questions, but yeah, I can't do that right now. But please do note questions down, and then we can talk about it Friday. I'll see you then.